Hi, I'm Eddie. Today I'm going to answer the age-old question, how does a wing generate lift?
We've all heard the basics. Well, it's because of its shape. You see, the typical wing has a curved top surface and a flatter bottom surface.
The greater curve of the upper surface means the air molecules need to travel further and therefore faster. This is explained because of the Coanda effect.
This is a tendency for a fluid that is moving to stick to a nearby curved surface. Air is a fluid, and it will stick to the curved top surface of a wing, which means it has a longer path to follow, and therefore it travels faster.
Now, according to Bernoulli's principle, faster moving air creates less pressure above the wing, causing lift. However, this is an oversimplification of what's going on.
For example, why does a symmetrical wing work? And how can a plane with a typical wing fly upside down? And why do our wind tunnel tests show that this curved wing shape will produce lift, but a wing of this curved shape will not?
The full explanation is a little more complex. If we place an object in an airflow, it will obstruct the air molecules, and they are forced to take a path around the object. This will create a congregation of molecules ahead of the obstruction with greater density and thus greater pressure. Also, correspondingly, there's a sort of void area of less dense air behind the object, creating an area of low pressure. Because of the laws of physics, all voids must be filled. This causes the surrounding air to fill the area of low pressure. We also see that there would be a lot of drag. Now let's look at a different shape. Here we can see the void where less dense air occurs above the object. There is compression of the airstream near the leading edge and a low pressure area behind, and it is this, according to the laws of fluid dynamics, that accelerates the airflow. The faster moving low pressure air is a primary cause of lift. Bernoulli's principle states that pressure in a moving liquid or gas varies with the speed of motion. In other words, faster moving air over the top of the wing will have low pressure. This causes lift. If we use a more curved shaped profile, we increase the efficiency. This is a typical airfoil shape. When we look at the wind tunnel tests, we can see that the airflow above the wing accelerates so much that it reaches the trailing edge well before the airflow below the wing. Bernoulli's principle is an important factor, yes, but it's not the entire story. The Coanda effect imparts a downward vector. When the air above the wing meets the airflow below, there is a resultant downwash. We see the airflow has been given a downward trajectory. According to Newton's third law, for every action there is an equal and opposite reaction. In other words, if an object in an airflow causes the airflow to deflect downwards, then the object will be forced upwards.
We can see from this picture that the wings displace huge amounts of air downwards and act like a plough through the sky. Newton's third law is clearly contributing to keeping this aircraft airborne.
Now what if we also incline the object in the airflow? The air molecules basically bang into the lower surface and are subsequently rebounded with a downward direction. This does two things. The downwash causes an equal and opposite upwards force on the wing, and this area of compressed high pressure air further contributes to the differential pressure between the top and bottom of the wing, and thus lift. We can see that lift is influenced by the shape of the wing, as well as the angle at which it meets the airflow, the angle of attack.
How do we change the amount of lift we get from a wing? And what is the best way to achieve maximum lift? Well, it turns out there's a lift formula.
Lift is equal to the coefficient of lift times half rho times v squared times s.
Let's look at each component. S is the surface area. The bigger the wing, the more it can lift. V is velocity. So we can see from the formula, this is squared. In other words, if we double our speed, we quadruple our lift. Rho is the density of air. More dense air has more molecules. And as the wing works by displacing molecules in air, thicker air amplifies this effect, and thinner air, high altitude or hot and humid air, generates less lift. The coefficient of lift is a bit more complex. It is a value that is dependent on the shape of the wing and the angle of attack.
Different shaped wings generate different coefficient values, and the greater the angle of attack, the greater the lift. But that's only true up to the point of airflow separation and stall, but that's for another video. We can also see how the orange symmetrical wing and the pink upside down wing can indeed generate a positive lift value. But the more typical wing shape, represented in green, will give a much better lifting performance.
So there you have it, no more mystery. We can thank both Bernoulli and Newton for the joy of flight.